double integrals over rectangles. From Calculus 1, we know that if we want to find the area under a curve, we can do this using what is called a definite integral. The idea goes like this. We have a curve defined on some interval from A to B, and we want to find the area under the curve on that interval. The way we do this, of course, is we divide up that interval into subintervals, n of them to be exact, and on each of these subintervals we approximate the area under the curve by finding the area of a rectangle by using an x value in that interval to find the height of the rectangle, and then we multiply it by the width, and then we add up all the areas of all those rectangles. And this is the sum that we get over here, which is called the Riemann sum. And if we take the limit as n goes to infinity, this gives us the exact area under the curve, which we call a definite integral. In this course, we are doing something similar. Z is a function of x and y, so our domain is in R2. Our function z equals f of xy produces a surface in 3 dimensions. And if we define a region, a rectangular region along the x and y axis, we can find the volume underneath this surface, but inside of this rectangular region. To do this, we take the rectangular region and we partition it on the x-axis and the y-axis. And this produces a grid. And on any one of these sub-intervals here, we get a little rectangle, and we can find the volume in that rectangle. So if you look at the rectangle there, we can find the volume by taking the width multiplied by the length, multiplied by the height. Now the width here is delta x, the length here is delta y, and the height is simply going to be f of some point in that box. So it is very similar to what we did in Calculus 1. Now if you do this for all of the rectangles that you see in this grid, you get something that looks like this. And you could find the volume of each one of these 3-dimensional boxes. And if you add up those volumes, this will be an approximate volume under the curve. So we define the double integral of f over some rectangular region R to be double integral, notice we have 2 integral signs here, over that rectangle of the function f of xy, and then dA stands for dx dy, basically. And we can do this as a limit of 2 sums as m and n go to infinity. Now we're not going to worry too much about this definition here. We're going to concern ourselves more with just evaluating these double integrals. So to put it a little more precisely, when we are looking for the volume under a surface on a rectangle in the xy plane, if your function is positive, then the volume V of the solid that lies above the rectangle is given by V equals double integral over the rectangle of your function dA. And again, dA is going to be dx times dy. To do these, we do something called an iterated integral. So when we integrate along the x-axis, we say the integral is from a to b. Integral along the y-axis is from c to d. And then we have our function, and we can either do the integration with respect to the y variable first, and then with respect to x, or we can do it with respect to the x variable first, and then with respect to y. Now, more precisely, this is what that would look like. But I really think the best way to understand this is to just do an example. So here I have the same integral listed twice, but notice the slight differences in the notation. So we have the same function x squared y, but here it's dy dx. meaning we're going to integrate the y variable first, and that goes from 1 to 2. And then we'll integrate the x variable second, and that goes from 0 to 3. Over here, we are integrating the x variable first, which goes from 0 to 3, and then the y variable, which goes from 1 to 2. So in this problem, it's important to note that x is a value between 0 and 3, and y is a value between 1 and 2. Now let's go ahead and perform the integration here. So this first method, we're taking the integral from 0 to 3, but first we're going to evaluate the integral from 1 to 2 of x squared y with respect to y. And then when we're done with this, we'll come back and do it with respect to x. So let's just focus on what's inside the parentheses here. If I integrate from 1 to 2 x squared y dy, basically we treat x squared like it's a constant because we're only integrating with respect to y. So this is going to be x squared multiplied by the antiderivative of y, which is y squared over 2. And then we're going to evaluate that from 1 to 2. And remember, 1 to 2 is for the y value. So this becomes x squared times y squared over 2 is going to be 2 squared over 2 minus, and then y is 1. We plug in 1, we get 1 squared over 2. So again, we just factor out x squared like it's a constant, and we plug in these values in for y, and then we do the math. So this is x squared times 3/2, or 3x squared over 2. So we now know that this equals 3x squared over 2. And it's important to note that, we don't put plus c or anything like that. So now we're going to finish this integral by taking the integral from 0 to 3 of 3x squared over 2 dx. And to do this, we are simply going to integrate. So we have 3/2 times x cubed over 3 from 0 to 3. This is x cubed over 2 from 0 to 3. And when you plug in 3, you get 27 over 2. Plug in 0, you get 0. So the value here is 27 over 2. Now we can also do it the other way. So the other way is what we have over here. And so that's going to be the integral from 1 to 2. And then first we're going to integrate from 0 to 3, x squared times y dx, and then dy. And so here I'm just going to focus on doing this integral first. So the integral from 0 to 3, x squared y dx. We're integrating with respect to x, so we treat y like it's a constant. The integral of x squared is x cubed over 3 times y, and this goes from 0 to 3. Now keep in mind we are integrating with respect to x, so these limits get plugged into the x variable only, and that is going to be 3 cubed over 3 times y, and then minus 0, of course, when you plug in 0, and so this is 9y. So now we can finish this problem by taking 9y and plugging it in for this integral here. And so this becomes the integral from 1 to 2 of 9y dy. And this, of course, is 9y squared over 2 from 1 to 2. And here we get 9/2 times 2 squared minus 1 squared, which is 9/2 times 3, or 27 over 2. So the point of this example is, of course, to show you that you get the same answer no matter which variable you integrate first. More generally, we can talk about Fubini's theorem, which basically says if you have a continuous function on a rectangle, the integral of that function can be done first with respect to y and then with respect to x, or with respect to x first and then with respect to y. So let's go ahead and do another example. Here we want to evaluate the double integral of the function x minus 3y squared dA, where the rectangle where x is between 0 and 2 and y is between 1 and 2. So we're going to define this as the integral of x minus 3y squared dA on the region R. And then we just need to decide which variable you want to integrate first. Sometimes it matters, but a lot of times it doesn't. So I think what I'm going to do is just integrate from 0 to 2, that'll be the x variable, and then integrate from 1 to 2, and then the function. Now, I said it like I'm going to do this second, but really this integral comes first, and that's the y variable, so we need to put dy and then dx. So we are going to do this one first. So this is the integral from 0 to 2 of, now let's figure this out. If you can integrate x with respect to y, x is a constant, so the integral of x is x times y, minus the integral of 3y squared is 3y cubed over 3, which is y cubed. And then we're going to evaluate this from 1 to 2. And then once this is all done, we will then integrate with respect to x. So we get the integral from 0 to 2 of, now keep in mind we are plugging these values into y only. So when y equals 2 here, we get 2x. When y equals 2 here, we get minus 8. Minus, when y equals 1 here, we get x. And when y equals 1 here, we get 1 cubed, which is 1. Now, once you do that, the y variable should be completely gone, and you can see that it is. So now let's just simplify this. 2x minus x is x, and negative 8 plus 1 is negative 7. So this is the integral from 0 to 2 of x minus 7 dx. And this, of course, is x squared over 2 minus 7x from 0 to 2. Plugging in 2, we get 4 divided by 2, which is 2, minus 7 times 2. And of course, when you plug in 0, you get 0, so the answer here is negative 12. Now you might ask, why is this negative if it represents a volume? Well, remember, the function f of xy, if it dips below the xy plane, you are going to get a negative volume. So it is possible for volumes to be negative, even though we know in the real world we don't think about volumes as negative numbers. But here there is a meaning for that. Now keep in mind, you could redo this problem if you want. In fact, if you want to do an exercise, it's a good idea. You could integrate this first with respect to x and then with respect to y. You would have to switch these limits around as well. But you should try that and double check to see that you can get the same answer. In the next example, we wish to evaluate the double integral of y sine of xy, where the region is the interval 1 to 2 crossed with the interval from 0 to pi. Now this notation simply means x is a number between 1 and 2, and y is a number between 0 and pi. And so this is the integral from 1 to 2 of the integral from 0 to pi of y times the sine of xy, and then this would be dy dx, right? dy would be first because that corresponds to this interval, and then dx would be second. Or I could set this up as the integral from 0 to pi, integral from 1 to 2, y sine of xy, dx, dy. So we can do this problem either way. If you look at it though, integrating with respect to y here would require integration by parts. And sometimes you have to use integration by parts, but I don't really want to use it if I don't have to in the very first integral. So I'm going to do it this way. Because here, if I integrate with respect to x first, I'm going to treat y like it's a constant. And we know from calculus 1, or actually calculus 2, that the integral of sine of a number times x, like sine of ax, for example, is equal to -1 over a cosine of ax. So we can use that fact here to do this integral. So again, I'm going to do this integral first. And so this becomes the integral from 0 to pi of, what is the integral from 1 to 2 of this function? Now again, y is a constant, so we'll keep the y. The integral of sine of a number times x is -1 over that number times the cosine of that number times x. So the integral of sine of xy is -1 over y cosine of xy. And this is going to be evaluated from 1 to 2. All right, so these cancel out here, which is really nice. And now if we plug in our limits, now again, remember we're plugging in for x because that's what we just integrated. This becomes negative cosine of 2y minus, and then when I plug in x equals 1, I get negative cosine of y. dy. And so now we can just take a little bit of time here to simplify. I can rewrite this as cosine of y minus cosine of 2y. I think that looks a little bit cleaner. And now the antiderivative of cosine of y is simply sine of y minus, and then the antiderivative of cosine of 2y is 1/2 sine of 2y. And this goes from 0 to pi. And so this is sine of pi minus 1/2 sine of 2 pi minus sine of 0 minus 1/2 sine of 2 times 0. Well, we know sine of 0 is 0. And we know sine of 2 pi is 0. And sine of pi is 0. So it looks like this entire integral is 0. Let's find the volume of the solid that is bounded by the elliptical paraboloid x squared plus 2y squared plus z is equal to 16. The planes x equals 2 and y equals 2, and the 3 coordinate planes. Okay, so here's the surface. This is the elliptical paraboloid. And then we have the plane x equals 2 is this right here. Y equals 2 is this plane. And then we have the xy plane, the yz plane, and the xz plane. And you can see clearly this is the volume that we're looking after here. So now to find this, we need to take the double integral of our function of x and y over that rectangular region. And so what is our function f of xy? Well, remember, that's the variable z. So if we solve for z, we get z equals 16 minus x squared minus 2y squared. And that is our function f of xy. So we're going to integrate from x equals 0 to x equals 2, and we're going to integrate from y equals 0 to y equals 2, the function with respect to y and then with respect to x. Now in this case, it doesn't really matter which one you put first or second because these are the same. But I'm going to choose to integrate with respect to y first. I don't think it makes much of a difference here. This will be equal to the integral from 0 to 2. Now let's integrate with respect to y. So integral of 16 is 16y. The integral of x squared is x squared y. And the integral of 2y squared is 2y cubed divided by 3. And we're going from 0 to 2, and then dx after that. So let's keep going here. We have the integral from 0 to 2 of When I plug in 2, we get 32 minus 2x squared minus 16/3. Okay, so keep in mind we're plugging in y equals 2. And now when I plug in y equals 0, we get 0. Now we can simplify this a little bit. 32 is the same as 96 over 3 minus 16 over 3 is 80 over 3. So we have negative 2x squared plus 80 over 3 dx. Integrating, we have negative 2x to the third over 3 plus 80x over 3 from 0 to 2. Plugging in 2, we get negative 16 over 3 plus 160 over 3. And when you plug in 0, you get 0. And so we end up with 144 over 3. And actually, I think that could be simplified. Yeah, so 3 goes into 14 4 times, and then 8, so 48. And the last thing is really just a comment. If you have a function of x and y that can be separated into the product of a function of x and a function of y, then you can integrate those separately and multiply the answers. But this is only when you have a product that could be separated. So for example, here in this integral, notice that the natural log of y divided by xy can be written as 1 over x multiplied by the natural log of y divided by y. So we can separate this into a function of x and a function of y. So if we can do that here, we can do these integrals separately. So we just need to remember that the y variable has limits 1 to 5, and the x variable has limits 1 to 3. So this would be the integral from 1 to 3 of the function 1 over x dx multiplied with the integral from 1 to 5 natural log of y over y dy. This integral here, of course, is the natural log of the absolute value of x from 1 to 3, which is natural log of 3 minus natural log of 1, which is the natural log of 3, because natural log of 1 equals 0. This integral here, we need to do a substitution. Let's let u equal natural log of y. du is 1 over y times dy. And so this becomes the integral of u du, which is u squared over 2. And if I plug back in my original function, I get natural log of y squared over 2. Now, you also could change your limits if you want. I'm just choosing not to in this case. So we have natural log of y squared over 2 from 1 to 5. This is going to be the natural log of 5 squared over 2 minus the natural log of 1 squared over 2, which of course is 0. And so it's just the natural log of 5 squared over 2. So our final value here is 1/2 natural log of 3 times the natural log of 5 quantity squared. And that concludes this video lesson.